Hello everyone, this is Mr. Jackson, and today we're going to be going through Unit 2, Lesson 2, Part 2, which is going to be over acids, bases, and pH. So this second part of Lesson 2 is really going to hit home a lot of key terms that we're going to need to build on in future lessons. And so we want to make sure that we clarify what we mean by these terms, and then we'll explain their importance as we move forward into real world applications like diet and exercise and just health in general and what we need to know from these. So want to go back and clarify some key terms that you might have seen a few of in Lesson 2, Part 1. We have added to this slide. So let's go ahead and clarify that whenever we use the term mixture, I'm talking about any material composed of two or more elements. Those compounds are physically mixed together, but they're not chemically combined. Okay, so a mixture would be something where there are two separate elements that basically remain separate even if we were to basically mix them or dissolve one in another. So that's the key thing. So a mixture is kind of like, think of like Chex Mix, right? Where I put a whole lot of things together in a bag, but I can still see the separate pieces within that mix. Going to review that a solution, whenever I'm talking about a solution, what I'm talking about is a uniform mixture of two or more substances. So in this case, one solute, like lemonade powder in lemonade, is going to actually dissolve out into a solvent, which is like what's doing the dissolving. So that could be water. And by diluting or dissolving lemonade powder into water, I create lemonade. And so that's what I mean by a solution. Just think of a solution. It kind of looks all like it's one thing because the powder has dissolved in the water. Sugar water, salt water, these are all really good examples where the mixture looks kind of uniform throughout. Now, a suspension is referring to a mixture of water and non-dissolved materials. Okay, so in this case, if we were to look closely enough, we don't actually see uniformity and a solute being dissolved, but rather we can actually see little non-dissolved materials. A really good example of that would be the blood that circulates through our body. Blood is mainly water, but within that aqueous solution, that water solution, we also have red blood cells, white blood cells, and little nutrient particles that are broken down being carried to the tissues in your body that need them. Now I want to go ahead and I'll go ahead and click through this so that we can see all of this. I believe that's all of them. But want to go ahead and clarify that sometimes water molecules can actually split to form ions, right? Those partially charged particles or ions. And so this is a reversible reaction. If you see right over here on the left-hand side, you can see that a water molecule can actually split to form a positive or a cation. We call that a hydrogen ion. And then it could also split into that other side, which is the hydroxide. So this would be an anion, a hydroxide ion. And this can go both ways. So these ions can come together to form water. They can split apart from water to form these two ions. And we are going to need to understand how water can break apart, because this is what's going to actually contribute towards what we call the pH level of a certain solution or substance. Now, you can look over to the right side here to the graphic, and you can see that I've actually provided what we refer to as the pH scale. Now, this is a scale from the number 0 all the way up to the number 14. And we have here that if something has a relatively high pH, it would be something like 7.1 to 14. We consider that a high pH, and those substances will be increasingly more and more what we call basic. Now, a base, to call something basic, means that this is a compound that produces more of the hydroxide ions in a solution instead of the hydrogen ions. So this is where you have increasing numbers of those negative ions. And good examples of these could be household soaps and household cleaners. Bleach is a great example of something that's very, very basic. And we also have the other end of that scale, the lower end of that scale, which would be solutions and substances that are more acidic. So this is where you'd have a higher concentration of the positive hydrogen ions rather than the hydroxides. Okay, so as we have more positive hydrogen ions in a substance, it becomes more and more acidic. So a really good example for acidic substances would be like citrus fruits or stomach acids, as an example. And very importantly, I want you to see that in this equation, right, water is just an equal combination of positive hydrogen ions and negative hydroxide ions, meaning that those positives and negatives in water actually cancel out. And so what that does is, because the positives and negatives cancel out, we actually consider pure water to be a neutral pH. A neutral pH has a value of 7, which you can see here on the pH scale. And importantly, the only other thing I'd like to say here with the pH scale is that as you get further away from neutral, like increasingly more and more basic to like a level of 14 or down to more and more acidic, like a level of 0, these are going to be substances that are better at eating away at other substances, right? So stomach acids, super, super acidic, and it helps break down the food that you eat in your stomach. Stuff like bleach, very, very basic, helps clean and break down any sort of grime that might be built up on household surfaces. And so finally, we want to finish up by clarifying one more term here, buffer. Okay, so now what is a buffer? We've talked a little bit about what it means to be basic or acidic. What is the pH scale? A buffer is going to be a relatively weak acid or a weak base that can actually react with stronger acids or bases, and this can help to basically prevent any sharp sudden increases or decreases in pH. So we don't like those sudden changes. Those can overload our internal stability, our internal balance. And so we want to have a ready supply of buffers that can actually decrease the overall effect whenever we have something, let's say, like an acidic food come into our body. We don't want the pH of our internal systems to change that much just because we eat a lemon, right? So buffers can actually work to decrease any sort of like what would otherwise be sharp increases or decreases in those pH levels. And so it's important to realize buffers dissolved in any of life's fluids actually go to help maintain what we call that homeostasis, those internal balances and internal stabilities in any living organism. And if you look over here at our image on the right, just as an important example, if I've got a solution here in blue that's very basic, right? There's a basic solution, and that basic solution does not have a buffer in it. If I add an acid to that solution, I am not going to be able to prevent any sharp change in pH. And so that unbuffered basic solution will become acidic overall, right? You can see how it changes color from blue to red. It's now more acidic because I added an acid. But if I were to have a buffer in that same blue basic solution and I add an acid to it, it can help resist any sort of drastic changes and keep the overall solution still relatively basic. And so that's what buffers help us do. They just help us resist big changes. And so guys, that was all we needed to do for lesson 2, part 2. Short and sweet, making sure that we go back, we understand those key terms, what makes something a mixture versus like a solution or a suspension, making sure we understand what we're looking at. If we're looking at a pH scale, increasingly more basic or acidic, what does that mean and what are some good examples? And then finally, the definition of buffers, all very, very important to know before we move forward into lesson 3. And so I hope that this was helpful, and we'll see you on the next one.